So for the lesson part of these videos, I thought I would go ahead and do the problem that I did in class, which was this one. So for all of the problems that you have for your homework assignment, you're supposed to go ahead and follow the steps 1 through 7 on page 228 to analyze the graph of each function. So we're going to use what we know, and we're going to analyze this graph or this function, and we're going to figure out if we can draw the graph of the function as well. So the steps on page 228 are: we find the domain of the function, and then we find the range. So that's the first step. So the domain. Well, we have to figure out the domain, we have to figure out, well, what x values would make this denominator equal to 0? So a lot of the same things when we're finding domain, like when we're trying to find the vertical asymptotes and things like that, we need to figure out what the domain is. What are the x values that make the denominator equal to 0? So, hold on, I had to pause real quick. Okay. Well, the domain would be all real numbers x such that x does not equal whatever causes the denominator to be 0. So x cannot equal 3 and x cannot equal -2. So there's the domain. We're going to save the range for later. I'll tell you why in a minute. The second thing we want to do is we want to reduce the fraction. Well, the fraction is already reduced. Okay, meaning you can't, there's no factors in the numerator and the denominator that we can cancel. So it's already reduced. Check. So that's the second thing you would do. Third thing you would do is you would find the intercepts. So we just talked about that in our last video. The x-intercepts occur when we look at the numerator and we figure out, well, what real numbers would make the numerator equal to 0? Well, if the numerator is always going to be a positive number, in fact, the numerator is always going to be 6. It's a constant. If the numerator is always going to be 6, then it will never equal 0. No matter what real number you replace x with, the numerator will never equal 0. Therefore, the fraction can never have a value of 0, which means the function never crosses the x-axis. Well, the y-intercept, we already know how to do that. We know that, let's actually use r. So r of 0, when we replace x with 0, we get 0 minus 3 in the denominator. 0 minus 3 is -3. And 0 plus 2 in the denominator is, 0 plus 2 is +2. Then we get 6 divided by -6, so we get -1. So if r of 0 is -1, then the ordered pair 0, -1 is the y-intercept. And that's all we have to do for that part. And we cruise on down to part 4. Part 4, we're trying to find the vertical asymptote, if there is one, or maybe there are more. There's more than one vertical asymptote. Well, if you remember, what we talked about is when we set the denominator equal to 0, whatever x values cause the denominator, what's that, the big equal sign, cause the denominator to equal 0, which are x equals 3 and x equals -2, then we have vertical asymptotes, unless the factor cancels. If it makes both the numerator and the denominator equal to 0, then we have a hole in the graph. Well, we don't have a hole in the graph here because 3 and -2 only make the denominator 0. You can, like if you look at the domain of the function, the domain of a function is closely related to either vertical asymptotes or holes, because the domain, wherever we have a vertical asymptote, that's going to be a real number that's not a member of the domain. Okay, so hopefully you can see the connection there. And then for part 5, or for, yeah, so part 5 of our analysis of this function, we have to find our horizontal asymptote, if there is one. And if you remember the Bubble Theorem, we take this the equation of the function. So we have r of x equals, I'm going to write that down here so you can see it. So r of x equals 6 over this. All right, so the degree in the numerator is 0. The degree in the denominator is 2. So therefore, the degree in the denominator is bigger than the degree in the numerator. So we have bigger bubble on the bottom. So the Bubble Theorem says that a horizontal asymptote, then, every time the degree in the denominator is greater than the degree in the numerator, we have y equals 0. So horizontal asymptote. So we have our vertical asymptotes, our horizontal asymptote, and that's the number there. When we have our horizontal asymptote, we want to go all the way back up here, and we're going to we're going to see the connection between, if we have a horizontal asymptote, then whatever, so if we're, then we're going to connect that to the range. So the range then would be all real numbers y, such that y cannot equal whatever that horizontal asymptote is. So for now, in these kind of more straightforward and basic rational functions, before you graph it, you can figure out, oh, we have a horizontal asymptote. The y value will never be equal to 0. And so then the range would be all other real numbers besides 0. All right. And so in fact, the range in general is better to find when you graph the function first. But anyway, if you put all of that together, we have a vertical asymptote at x equals 3. There's one vertical asymptote there. We also have a vertical asymptote at x equals -2. So we're going to put everything together. It does say that you should use Desmos, and that's what I do suggest after you try it on your own. Y-intercept of 0, -1. That would be a y-intercept there. No x-intercepts. And the thing with rational functions, which you'll start to get more familiar with, is they are made up of polynomials, and so they're nice and smooth and continuous, except for when there's a break in the graph. And the break in the graph for rational functions will always be either a vertical asymptote or a hole. So in other words, the domain is all real numbers until you get to that spot, and then all real numbers until you get to that. Oh, you didn't see that. So all real numbers, the graph is continuous until you get to -2, and then continuous until you get to 3, and then continuous forever. So that's kind of what if you look at just a kind of left to right perspective, the graph of this function will be continuous except for those two values. And the asymptotes, I forgot to draw the horizontal asymptote of y equals 0. So the horizontal asymptote y equals 0. The graph needs to go towards those asymptotes. So we're going to start with the only one point that we know of is this one right here. You can't go up to that asymptote because then you'd cross the x-axis, and you can't cross the x-axis. So you have to go down to that asymptote. Then you also have to go to this next asymptote, and you can't go up there because then, again, you'd cross the x-axis. So you have to go down to the asymptote. So you're going to go from asymptote to asymptote, not crossing the x-axis because we don't have any x-intercepts. Now, the next part is, do we go up here, like up here, or do we go down here? Well, if we replace x with, so we're going to put it down here again. If we replace x with a bigger number than 3, like 5, you can look at, and if you replace x with 5 in both of the factors in the denominator, you're going to get a positive times a positive, and the numerator is positive. So anyway, the numerator is positive, so the whole thing, when you replace x with 5, you're going to be up here above the x-axis. And so since you're up there, you have to go from asymptote to asymptote, and you have to stay above the x-axis. And then likewise, if you replace x with a number to the left of -2, let's say -10, you get a negative times -10 plus 2 is also a negative, and two negatives multiplied together give you positive, and again, we're going to be above the x-axis. So when x is -10, you're going to be above the x-axis, and if you're above the x-axis and you don't have any x-intercepts in there, you have to stay above the x-axis. So they're always going to be nice and smooth and curved like that, and you can double check that with Desmos. And there you have it.